Hello friends, welcome to another video in the playlist of analog electronics. Today we'll talk about the concept of virtual ground. This is so very important to understand this concept in operational amplifiers because if you understand this concept, you will be able to solve the numericals in no time. So let's get straight into this. In order to understand the concept of virtual ground, we need to see what a differential amplifier is and how does it work. So for an ideal differential amplifier or an op-amp, we know that the input resistance is infinity, the output resistance is zero, and this gain is very high or infinity. That's the case of an ideal amplifier. And by the way, the concept of virtual ground also holds true for an ideal amplifier. Now, what is the underlying rationale behind it? We need to understand that. What happens is you get the output voltage to be equivalent to A into V in. So you would want this amplifier to amplify a very, very small voltage given at the input and amplify it to a level which is well within this limit. You'll see that every operational amplifier will have these two limiting voltages, plus 12 and minus 12. So no output can go beyond these two voltages. So if you wish to keep your voltage limited between these two voltages, for example, if you wish the output to be 5 volts, and an effective amplifier would have been to take a voltage at the input of the order of millivolt or microvolt and multiply it many times and take it to 5 volts. That would have been an ideal characteristic of an amplifier. So how is that possible? So if you look at this formula where the gain of the amplifier is V0 upon V in, we want this gain to be very high and we want the voltage difference between these two to be very small. Only in that case we'll have V0 to be very high. Now let us say we want the output to be 5 volts. For 5 volt output and for a gain of, let us say, 10 raised to the power 6, we want the input voltage difference 5 divided by 10 raised to the power 6. So that will be 5 into 10 raised to the power minus 6 volts. Now this small difference of voltage between these 2 points, V1 and V2, is almost tending to 0. And when there is no voltage difference between these 2 points, we would say that these 2 points are virtually at the same potential and they are shorted. However, in case of a shorted scenario, otherwise in network analysis, there would not have been a resistance between them. But here the resistance is infinite. So this point is super crucial to understand, that even though that there is a humongous resistance between V1 and V2, these 2 points are at the same voltage. And why is that? Because of the overall structure of the overall functioning of the operational amplifier, because the operational amplifier is designed in such a way that the difference of these two voltages needs to be very small, of the order of 0, in order to get a very high amplified voltage at the output. If we want this thing to be extremely large and we want this thing to be restricted to plus 12 and minus 12, let us say plus 6 or plus 5, then that could only happen if the difference between the two voltages at the terminals is kept as small as possible or to be equivalent to 0. So this is the main point of understanding, that these 2 points come at the same potential because of this whole working scenario of operational amplifier. And once you understand that, rest everything is pretty simple. Now if you look at this case where we have this as the negative terminal or this as the grounded terminal, and we have, let us say, this as the feedback, this is output voltage and this is, let us say, the input voltage. If you apply this concept, we see that because these two are at the same potential, so no current will flow here, no current will flow here. This is extremely crucial point. No current will flow to plus or minus. And at the same time, the second concept is that the potential at this point and the potential at this point, they are going to be the same. So V1 will be equivalent to V2. And incidentally, V1 is 0 here. Now this 0 is actual ground. V2 being equivalent to 0 because V1 and V2 are the same is known as virtual ground. So this point is not connected to ground directly. This point does not have a zero potential directly. However, this point and this point are at a negligible, very, very minuscule voltage difference. So that is why we say that this point V2 is also at zero voltage and it is known as virtual ground. Virtual means something not happening in reality, but it looks like it is real. So it looks like V2 is connected to 0 volts, but it is not. It is equivalent to V1 and that is why it is assumed to be 0. And if you understand these 2 points, then solving these questions becomes super easy. Let's see how. We know that according to the second point that no current will flow and the voltages are same. We know that no current will flow here, the voltage here is 0. Then the only path for the current from this voltage, input voltage, will be to go from, let us say we have this input resistance Ri. So the current will flow through this input resistance and will go to this path to the output. Because the current cannot go here or here because of the zero potential difference. So the only way for the current to go is through Ri and then to Rf. So what we can do is the potential at this point is 0. So we can say starting point, potential at the starting point is Vi, potential at the end point is 0. Potential difference upon resistance is my input current I. And also this I will flow here. So the starting point of I is 0 and the ending point of I is V0 upon resistance Rf. So minus V0 upon Rf is also I. So this is also I, this is also I, and we can compare these two. We see that Vi upon Ri is equal to minus V0 upon Rf. This is Rf, by the way. So we can easily calculate V0, which comes out to be equivalent to Rf upon Ri into Vi with a negative sign. And this is nothing but the actual formula for the operational amplifier. How cool is that? So whenever you see an ideal op amp, what you need to do is you simply need to find the potential at this point, because if you can find the potential at this point, the potential at this point will also be the same. And then the second step is that no current will flow here, no current will flow here. The only way for the current is through input resistance to this path. So if the network here is expanded, or if the network here is expanded, that makes no difference. So that will technically make it a network analysis question, because you simply need to analyze this network and of the network find the current here and then send it here, and you need to calculate the voltages at different points or at the output. So technically it becomes a simpler question of network analysis, no longer a question of operational amplifier. So this is the concept of virtual ground, that the potential between V1 and V2 is so negligible that we consider them at the same potential, and if one of these terminals is connected to ground, then the other one also takes up a zero value of potential, which is not technically true, but virtually it is true, and that is known as virtual ground. So I hope this tutorial was of help. If you liked the video, give it a thumbs up. I'll come up with numericals on the same topic in the next video. Till then, take care. Bye bye.